Well, first of all, let me thank all the organizers. Very glad and honored to be here. It's an interesting meeting. I hope to help you, during your digestion. I changed a little bit my title. Actually, the concept is the same. What we're going to do here is to discuss whether the Mantle can contribute and how can contribute to the Mantle building. So this is the work we are doing during the last few years with colleagues and friends, basically Thorsten Becker and Clint Conrad and Laurent Son. So during the previous talks, we heard that the importance of mantle convection in shaping and as a dynamic engine of our Earth, and we are pretty sure that it represented the plate tectonic engine. In fact, during the last decades, several people will try to understand how mantle convection can drive plates, and successfully, there is a plethora of models, for instance, using tomography, inverting tomography, seismic tomography for density, how to have convection and measuring the velocity of the plate and doing quite a nice job here. I recall just a couple of papers, but there are a number of that. Other people trying to make another exercise, Carolina and Clint, for instance, here, trying to, using the history of subduction in the last 100 million years, inverting that for density. And as well, in this case, the match is fairly good. And this is good also, especially for the case of large oceanic plate. Things get more complicated when we move down into the continent. Here, in fact, we don't really know, and the pattern of convection we are expecting is more uncertain. For instance, I just show you, for comparison, two models that running for understanding the vertical motion of the Colorado Plateau. And on the left, you have, for instance, Mucha et al., where he claimed for vigorous wall mantle convection explaining the uplift of the Colorado Plateau, whereas on the right, you have other approach that is explaining the same process just by small-scale convection confined in the asthenosphere and relative instability. So because of that and because of the continental lithosphere present inherent and intrinsic heterogeneity in the lithosphere, and because it's moving slowly, the pattern of convection beneath the continent is more uncertain. So today what I would like to discuss with you is basically where is the role of the mantle in doing mountain building? Is there any role? Does it contribute? And can the mantle explain the fact that we have enormous mountain like the Tibetan Plateau? So I'm trying to, my main message will be that yes, the mantle is important, and we are facing with a multi-scale convection pattern that is pretty complex. And so to try to convince you that is the case, I will bring you to a journey in the Tethyan Mountain Belt, which is a long-running belt running from Spain down to Sumatra, basically, and try to reconstruct the pattern of mantle convection, both at local and at more large scale. And to do that, I will use plate reconstruction, geodesy, but basically tomography and modeling. So this is the first geological map that we're showing here today, which I'm pretty glad to do that. Is the Tethyan Belt, looking from this is a Manuel Poubelier map, very nice, and the colors show the age of deformation. And what you can appreciate here is the fact that the Tethyan Belt is a long-term the belt that deform accreting blocks in different ages. So in the blue is the Paleozoic, then you run into the Cretaceous tertiary block, and then you run onto the Cretaceous in green, and then the yellow is the tertiary one. So it's a diffuse plate boundary accreting block over a long term. And this is well reflected also by seismicity. The seismicity is diffuse over a wide area. This is very well known, and is only in very few sites is concentrated and giving deep earthquake, like in Calabria, in Pamir, or in Sumatra, where you find only trace of Badati Benioff zone. And this means that probably the collision is going on for a long time, and so you don't really have any subduction zone really going. And this is well reflected also by the geodesy, with the yellow arrow are the GPS velocity with respect to Eurasia reference frame. Here you may see that the nice pattern of indentation, which is the kind of entrance of India inside Eurasia and Arabia inside Asia, at different velocity. India is going at about 5 centimeters per year, that's the scale on the left, whereas Eurasia is going a little slower. What is also very interesting to see is this kind of symmetrical pattern, although with a general increase in the velocity, with an escape of material toward the Hellenic subduction zone, in the west, and in the east toward the Sumatra subduction zone. The formation, again, is spread over a large part of the Eurasian continent. So, how about the kinematics of this region? Well, basically, we know pretty well the motion of India, although Dow recently gave out a constraint on that. We know that basically all this game is played by the closure of this ocean. This was between India and Eurasia, and Arabia and Eurasia, which is the Tethys. But what is really interesting when you look at this curve, for instance, which is the velocity, basically the northward velocity of the India-Adria plate, which is stuck in between in the Mediterranean, and Arabia in different color, is the fact that India show a peak in velocity, which is very sharp. Everybody acknowledge that, over 15 centimeter, about 65 million years, and then start decreasing the velocity at the time probably the collision. But what is very interesting also is that since the collision, the velocity keep constant. And this is very bizarre. And this is the same game, although without a peak in speed, happened for Adria and happened for Arabia. That is, at the time of the collision of Arabia, around 30 million years or even younger, its velocity keep constant about 2 centimeters per year. So we are facing a protracted collisional phase. Something have to push even after collision this plate against the other. So what are the forces at work that we may imagine working in such a system? Those are basically the suggested force, and in its classical force coming from the 60. The first one is lap pool. Even in continental collisional setting, you may have that the mantle lithosphere can delaminate from the crust and can go down. It's denser, so it may pull the slab downstream. Then you have the ridge push, which is of course a GPA force, a difference in gravitational potential energy between the ridge and the rest of the oceanic plate. It tries to, of course, push the plate. Then we have other two forces here. It's probably the same thing, but maybe not. I don't really understand that. But in any case, one can be the mantle flow. A mantle, large-scale mantle convection can drag plates, so can exert a force, and also via slab suction can shear the plate and drag the plate. Or you can have a sudden plume that is arriving on the surfing and pushing the plate. So let me review fast. So to have collision and to have Tibet, where the crust arrived to 90 kilometers, then you have that all this force, the force, should be at least equal to the crustal thickening force, which is the resisting force. You have to sustain this mountain, which is a big effort, and then to overcome the resistance of the shear along the thrust fault, and those numbers for this resistance force arise to almost 10 to the 13 newton per meter, as estimated by, for instance, Gauss and Husson. So let me review first quickly what is the contribution. Slab pool is, of course, is important, is interesting. If you scrape off the crust, then it fits fairly well. This is the velocity, this is the time. The decrease in the velocity of the India, so it can be used as an argument to say that the decrease in the velocity of India after collision, as Fabio Capitano proposed, can be explained by the reduction of slab pool in time, but it cannot really explain the protracted velocity of subduction that you have afterwards, the 5 centimeters that we have today. Also because most of the tomographic images beneath India and beneath Arabia clearly show no connection or complete detachment or very small slab attached, as in this model by Leo, by Wim Spackman, from the deep part of the slab to the shallow one. So very few slab pool expected now to work in this area. A ridge push, it can be contributed, of course, but it has been demonstrated that you need other additional north-south force, for instance, in this model by Ghosh et al., to create compression in Tibet. Otherwise, the Tibet will collapse and you will have extension. This is white stick that show the orientation of extensional direction. So this model, only driven by ridge push, cannot fit in any case neither geodetic nor ecosysmic deformation you observed. Plume push is a very interesting argument that's been proposed a long time for Laurentia by Maggernis et Trond. It has been recalculated now for the case of India. It is, of course, by Weinisberger et al. and reproposed by Candia Stegman as well. I think it fit first order argument, the fact that the speed, the high peak and velocity that we have in India, is correspond to the emplacement of outpouring of the Deccan Leap, so it's good. I mean, of course, we should take into account that. But what is interesting from the modeling show that of Weinisberger et al. Is that this can explain fairly well the peak in velocity and also the decrease in velocity, probably, but it's probably too weak to keep going for the productive velocity of India, and it should expect to have only a temporary effect. Although it might have weakened a lot at the base of the lithosphere, I think this is a very interesting process that we have to explore by emplacement of low viscosity material, lubricating the base of the lithosphere. So, ridge push probably is not enough. Slab pull not enough. Plume push, yes, but only at the time you have this peak in velocity. So whatever else. We may think that large-scale mantle flow or continental underthrow can be an effect, and we start. I will try to show you how it can work in this system, looking first in the Mediterranean area, and then going more in detail into the entire Tethyan system. So the Mediterranean here, again, red, the dots show the seismicity, the yellow arrows show the velocity in GPS. You see that the velocity increase toward the east as the seismicity does. Also, you see that very few deep earthquake, only basically in Calabria. What is interesting is to see that, as you may notice, that this is an important issue for Mediterranean tectonic, the fact that the Anatolian plate is moving westward about 3-4 centimeters and accelerating the Aegean. So irrespectively to the overall convergence frame that here attain only 1 centimeter between Africa and Eurasia, you have this increase in velocity here, and also Adria is moving independently. So what happened here? There is a number of reconstruction. This is basically our field area, so we pretty know very well now what happened. You do imagine that once upon a time, at 35 million years, you have a long-running subduction zone in the Alps and in the Betics and in the Hellenida. And when continental macroplate arrived to trench, which is Adria, then it was progressively consumed by the advancing on trench, arcuating, forming the Bekark basin here, and the Pannonian, and arriving to the present-day setting, where you have only small pieces of subduction zone that are preserved. And this is pretty well known also by tomography. You see that high velocity, which is here, is very well resolved. We will see the patch of high velocity anomaly here, Alps, the Dinarites, Calabria again, Africa, Hellenites. When you go deeper into the Mantle, these patchy broken slab merge together, and when you arrive to the 660 discontinuity, you find the trace of the Tethyan Ocean actually here, stagnating on the 660. But going only beneath the Hellenites, you have trace of penetration of the slab. In this area, basically, everything is impermeable. So the effect of this process is pretty well known in the Mediterranean, the Central Mediterranean. We have these two big Bekark basins that are produced by the rollback of this trench here, and this is the tomographic image that you will come out. So finally, you can Mickey Mouse cartoon as said yesterday, to imagine how you arrive to this present-day setting. First, you had the large subduction zone broken in pieces of piece, and then dramatically lose part of its coherence, so sharply producing this enormous back tension in very short time, produced probably by small-scale convection. So how can we test that? Well, in Rome, we are pretty good on doing laboratory experiments to try to unravel the evolution of a subduction zone and a convection pattern in the mantle. But this kind of process requires probably a more sophisticated solution or different solution, more complicated. So I knock on the door of some of my friends and I say, can we do that, something for that? And yes, we try to do our best. So that's our best in terms of mantle convection. It's a global convection model where we impose a number of assumptions, which is some of them are very pretty strong, actually. So, of course, we have to solve Stokes flow solution for an incompressible flow. As a boundary condition, we use a surface and core-free slip. The rheology is oversimplified with the layered viscosity structure, but we include the lateral viscosity variation. At least we assume a Newtonian fluid, and we impose the plate boundaries, which is imposed as a weak plate boundary. The model to run, we have to make some decision, and we have to invert the density anomaly, as in tomography, into temperature. So we decide, and I hope that Alan and Paul will not get too angry, to convert directly all the velocity inside in density, considering no chemical anomaly beside the continental kills. This was a forced choice because of the amount of thermochemical perturbation, at least in the deeper layer of the mantle, are still pretty uncertain in a way. So, although some tests that we have done can demonstrate that easily that for the Africa and for the Tuso and Jason low velocity zone does not influence too much the velocity of the plate on the surface. So boundary condition on this one, we take tomography, several tomography models. Now we take this one, which is the model by MIT, for instance. But we test also other models, and we impose the plate boundary here. And what we impose here, you see the orange arrow again, the GPS velocity with respect to Eurasia, and the gray arrow are the velocity of Africa and the Arabia with respect to Eurasia. So basically, our result we'll try to do the best resolution we can. Using a very high resolution tomography here, and we can compare our result with the plate motion on the surface within the Mediterranean and with the dynamic deflection of the surface. So we can compare what we expect, and we call dynamic topography, which is the topography not related to the isostasy, but related to the motion of the mantle. So this is one of the solutions, and what we're going to discuss. Again, the orange are the GPS, the gray are the velocity of Africa and Arabia, and the white are the result of our model. So those two macroplates, Anatolia, Aegean, and Adria, are left free to do whatever they want. The gray are the plate boundary, and the background flow, the background color, represent the upwelling and downwelling area, basically the dynamic topography. So red is positive, there is the scale in kilometers, and blue is negative. So what you can capture here at first sight is the fact that, well, we have a large scale upwelling here in the east. We have the velocity of Anatolia is good, it's pretty good with respect to geodesy. We do not match at all the velocity of Aegea. We predict fairly well the southern motion of the northeastern motion of Adria here, and we do not catch at all the motion of Adria here. But what is very interesting to notice, if you do a cross-section from the Near East to Hellenic slab, Calabria slab, and then France, you have this kind of pattern. So the large-scale upwelling here, flow is arriving from here, is flowing at the base of Anatolia, dragging Anatolia a little bit, then going to the Aegean slab at a high angle because it's rolling back, and then it's going up again beneath Adria, and then going back again in the Calabrian slab, and then going up again. So what is coming out of this picture is the fact that if you have enough resolution out of your tomography, you can capture the scale of convecting cell which is about a couple of hundred kilometers. It's very small. And you can have a feeling of what's going on at depth by these slides. This is at 250 kilometers, for instance. The red is upwelling, the blue is downwelling, and you have this large-scale toroidal flow arriving from the east that is going inside the Aegean slab here, where the slab arrives to the lower mantle. And also, again, blue and red, all patchy localization. And when you go deeper, you find trace of this upwelling and downwelling, but the lateral flow is keep more continuous. And when you enter into the subduction zone, at the bottom of the upper mantle, everything flat down, and you have only the Aegean slab penetrating. So it's just something that we are busy looking at, something that is basically confined from the base of the lithosphere to the top of the transition zone. Okay, then we can get better, we can make a lot of tests. I'm not going into the tail of that. What is interesting, for instance, if we stop Africa and Adria, then you have this arrow here. The result is showing that part of the Anatolian motion is surely dragged by the mantle, partly is probably pushed by the Arabian indentation, but a large part, up to 60% of this motion, can be explained only by the mantle. And also, when you decide that the alpine belt subduction zone is dead as it is, you probably can improve also the solution for Adria's slab. Well, interestingly, the Mediterranean show very sharp topographic contrast, a big, deep basin, for instance, in Calabria, and half mountain that are uprising, but also out of the boundary, like in Iberia, you have area that is uplifting, and Anatolia and Iranian. So is there any signature from the dynamic topography? Well, this is the residual topography. What is that? It's just we eliminate the isostatic component of the crust out of the topography. So the crust is not here. The isostasy of the crust is eliminated. And this is what is left. So all this patch should be topography that is related to the mantle, either lithosphere or sublithospheric mantle. And you can directly compare it to the dynamic topography image that we have. And this gave interesting insight. For instance, the scale, of course, is out. I mean, the scale here and here is very arguable. I mean, it's just number that you put, so you can handle with that. But what is interesting is that the trend is positive here. For instance, reflecting this large-scale uplift here, Anatolia, pretty sure that there is a dynamic topography effect here, but also in Iberia. And then you can go in the field and looking, for instance, trying to understand why you form the mesetas here in Iberia, and can explain that by this local upwelling with just a few hundred kilometers. And also the Iranian plateau probably is the case of dynamic topography, and the Anatolian plateau as well. So what can we capture out of this example? This is a cartoon showing what we imagine, a large-scale mantle flow in the Mediterranean, coming from the Arabia probably, and entering to the Mediterranean and sinking into the Aegean slab. Apart from this large-scale flow, everything is very small scale. So there are two multi-scale system that is working together, and this can explain the sharp and intermittent pulse of extension and the tight arc that you form in this complex setting. So let me zoom out and going to a more regional solution. So here the case so we are doing the same exercise basically, but encompassing the entire area from the Aegean and going to Sumatra and Java. So this is the boundary condition we are using. We are imposing a weak zone here, distributed here, that are following the major deformation zone as depicted by seismicity and mechanism, basically, focal mechanism, seismicity. And on the base of that, we run our model. So the first thing to do is that we use S-mean, already discussed with Trond. It's an average model, so we want to be sure that it's a stable model, but we test several other models. The second thing that you can see already from this model is the fact that the shallow upper mantle depth, you have two upwelling zones. One is beneath Afar, this is pretty well known. Another one is beneath the Carlsberg Ridge, and this is pretty well known as well, but a very important pattern. And then you have this low high velocity zone, which is reflecting the Tethyan slab. Here it's very smoothed out, but it's in other P-wave model are more so, and I will show that. And I will also remark your attention on this point. What we were looking before was this one. This is the resolution we have in the Mediterranean because of course, we are in Europe. We have a lot of stations, so we can do a very good job here. And this is the resolution we have when you go over the globe. So the scale of mantle convection we are expecting, it should be very dependent on the scale of data that you put inside the system. And so it is important to take into account that. So those are the results. I hope you can see the coastline. It's really little behind. This is Africa, this is Arabia, this is India, is beneath the arrows. So this time all the plate can move whatever just under the excitation of the mantle convection. So again, the orange are the GPS velocity, whereas the white are the solution out of our model. Everything is compared to for a region fixed reference frame. So we are pretty much satisfied by the result, especially when you look at India. Actually, India is moving in the right direction, and is doing a very good job here, basically, but is not matching at all this return flow to Java Sumatra, which is completely unmatched by our model. Arabia is also doing well, although it's over-predicting the velocity here. We run also some model where we do some better solution. So we are right to have a very good regression here. Again, very bad solution is for Australia and for Africa. And Africa, for instance, is going in this direction. I would like to make up the point before going on commenting that. We haven't done any effort really to match properly the velocity of the plates. It's just the result. There are other models that just focus on matching the plate, so tuning the viscosity and tuning the density scaling just to match the plate. Those models is very crude in a way, and rude, just to see what are the main driving mechanisms behind. So Africa is not working, really, it's going in the wrong direction. Australia also is not really working, but we test that the influence of this plate, which is moving pretty slow in our case, doesn't make a big difference in terms of interaction with the Arabia and Africa. We run model especially to demonstrate that. So we can go deeper as we have done previously. And what you see here is that you have this low velocity anomaly here in the Carlsberg, low velocity in the Afar, well known, and so the pattern of velocity that you expect is going from this low velocity anomaly to the high velocity anomaly, which is the Tethyan belt, and going again here. And when you do cross section here, for instance, this is Arabia, you may see the pattern of Afar plume rising up, pulling the Arabia's plate toward the subduction zone, which is here. And you have the material that is broken and is falling to the lower mantle. And so this produces a conveyor belt encompassing the whole mantle, but basically centered also in the uppermost part, the middle part of the mantle at least. And this conveyor belt can produce this kind of flow and velocity in the surface. And similar, but even more pronounced, is for the India. You see Carlsberg Ridge here, rising, upwelling fluid, and then you go down, and this is the Tethyan belt, so you go back. So a large-scale conveyor belt. And this can explain, well, how India is, in this model, is going north, and is colliding. So a surface effect, again, as in the Mediterranean. Dynamic topography, this is the residual dynamic topography, again, the topography out of the isostasy and the crustal isostasy, and you may compare that with what the model prediction do. Fairly good in mapping out the Afar system, the dome, the Afar Arabian dome in Kazbek is okay. You also find a very good correspondence with Iron Plume, with Mongolia again, and also some depression that you expect over the subduction zone. So it's not too bad, although the correlation is low, and it's basically due to the fact that we cannot really correctly match the surface topography over Craton, and this is a long-standing debate, actually. So, what is really interesting? This is the model that we used as mean. Can we use another model? For instance, if we take Lee et al. Already proposed, this is a Vanderlist group model. It's fairly well. It describes fairly well at 250 kilometers depth, more or less, the position of the high velocity anomaly. It fairly well the Afar plume, but there is no Kazbek ridge here. Okay? So because this is a limited intrinsic problem of the P-wave model, it doesn't capture fairly well the low velocity anomaly. And if it's the case, then India is not moving anymore. So it's moving just a little bit on the other direction, and also Arabia is not matching anymore. So only if you include the low velocity anomaly, that is the upwelling part of the system, you may match the velocity of these colliding continents. So let's go toward the summary. I'm running very fast, so maybe I have some time, but yeah, sure. You can save some time with me. The summary is that what is the role, and I think we be able, just matching the present day pattern of convection and velocity, to match fairly well the velocity of this colliding continent over this large scale. So we think that the slab effect, slab pool, can be insufficient, as already been proposed by other authors, to drive India in the right direction. But slab suction does. I mean, it's an important component. We think that the active component upwelling of the system here is a temperature profile over a cross section. Here you see the African superswell or low velocity, large low velocity shield zone upwelling here, and it's rooted into the Afar and the India. I think that this component for Afar and Kazbek ridge are fundamental, otherwise India is not moving anymore. And so in this case, we can explain as with a conveyor belt the plate motion and dynamic topography of India. We couldn't explain at all the large scale, either in the Aegean and in the Indonesia, escape to a southeast motion of the material, this toroidal flow. This is perhaps due to the fact that this model did not include any GPA. So, and also the crust. There is no crust here. So maybe including that has been proposed by other people, we may have this kind of pattern of outward convection. So let me zoom out a little bit more now to a more global solution. This is what we have shown today. So we start from the Mediterranean, we look at the Tethys. So this is the high velocity anomaly related to the Tethyan belt, a very nice suture in the mantle, and for us geologists, I think it's a very striking argument of what happened. And this is the rising up, the shallow and the mid-mantle, upper mantle of this upwelling area in the Afar and in the part of the Africa. It's also interesting to know that on the other side of this large-scale upwelling area, you have the Cordillera, and we knew that. So we are facing some system which is locked between one subduction zone and the other, and Alan was mentioning that before. So if you do a cross-section here, you have this, and this has been also in textbook if you find. So this classical that Alan was mentioning, bipolar, and also Trond was mentioning, very simple degree 2 configuration of the system, where you have African superswell from one side, Pacific superswell, and the two blue anomaly here. One is related to the Tethyan belt, this is the Pacific subduction, and this is the Cordillera. Now what we can do also is try to we can draw some this big large-scale convection, and we can do for simplified cell. Although in plan view this is a complicated job. So concentrating on the upper side of our Earth, we can also, doing an exercise, we can position in the position of the trench in time for the Cordillera, for instance, and for the Tethys. And this has been done also by other people before us. So trying to envisage or to understand when the material was entering to the lower mantle. This number are, I don't know whether you can see that, 90, 70, 50, the trench or during the opening of the Atlantic and the American rollback here. So what we have found that the position of the trench at 90 is here, the low velocity, the high velocity anomaly is here. Therefore, to arrive a good match, we have to expect at least 50 or 40 million years. That is the maximum age of penetration of the slab into the lower mantle. And you can do the same exercise here, and many people have done that before me and found that probably the onset of subduction into the lower mantle in India and the Tethys is around 60, 65. And this matches fairly well the acceleration of India. So if you do this job, then you have to imagine an evolution of this system which cannot be like that before. Should be different in a way. And so this is something that we are working on. It's a really Mickey Mouse cartoon. It's starting from the mantle convection pattern that we can reconstruct from model. And this is what you see. This African superswell. This part is playing a lot of the game in the place velocity. And you may reconstruct one convection cell here that is branched with a Tethyan slab and here. But when you go back in time, at the 60, 70 million years ago, the Cordillera slab was not penetrating to the lower mantle. There were probably already material, but it's related to some other process or older process. And mostly, the Andes was not here, because at 60 million years, all South American plate was under extension. And the Andes start rising up at 40 million years. So what is interesting is that we have to imagine that about 60, 70 million years, you start having this large-scale convection cell working with the high velocity anomaly dripping down to the lower mantle, and you have the Deccan leap that it was outpouring on the surface. You have to wait for about 30 million years, because this cell also in the South America keep going vigorously, and at this time, so the South America can be pushed against the trench, the slab can be anchored into the lower mantle, and then you can start creating also the Andes. And so arriving to the present-day solution. So I'm running to my conclusion. Of course, this is just a scenario where it can be interesting to discuss altogether. My conclusion is basically this one. First of all, depending on the resolution we have, we should imagine that at least beneath continental plate and mobile belt, we should imagine that a multi-scale style of convection. So it's a very small convection cell concentrated at the base of the lithosphere and embedded within a larger scale convection. We think that moon mantle convection is necessary between Africa and India to explain the persistence and the protracted collision of Indian plate against Eurasia. Otherwise, the volume force, GPA, will take place and you will never create 80 kilometers of thick crust in Tibet. Similar setting, I think, can work out also for the Andes, although a couple, 20 million years before. And the anchoring of the slab into the lower mantle can fix the trench, and with a vigorous mantle convection, you can rise up also the other mountain belt system. And I think that if it's true, we can use the mountain building to really decipher in the geological record can be used to identify episodes of vigorous mantle convection that take place. And this is the real conclusion anyway.